and welcome to Aerodynamics for Pilots. This series of lectures is aimed at private pilots who want to have a deeper understanding of how and why their aircraft behaves as it does. These lectures are not part of any course and are not designed really to help you pass your private pilot's exam or commercial pilot's exam. These are more basically just interest. We have four lectures in the series: lift, drag, performance, and stability and control. Anybody recognize this picture? This is from over 100 years ago, and it's the picture of the Wright Flyer on its first flight at the Kill Devil Hills. This was done after years of research, much experimentation and analysis, and it was all self-funded. The first lecture is on the topic of lift. I promise no mathematics, but for completeness there are a few concepts I want to introduce so that we have a clear idea of what we're talking about. The first is Newton's second law, which you may have heard of as force equals mass times acceleration. It's actually a bit broader than that. Force equals the rate of change of a quantity called momentum, which is mass times velocity. So that's momentum, mass times velocity. And when you change that, you get a force. If you have something hard to push against, force is easy. So pressing against a wall or a floor is easy and free. You can push as hard as you like against something rigid. But when you don't have a nice hard surface, you have to use Newton's second law to produce force by a change in momentum or a change in mass times velocity. Aircraft use this law to provide the forces that hold them up, and of course also to provide thrust. Another concept I'd like to introduce is the concept of Q, defined as half the density times the velocity squared. Q is a pressure, also known as dynamic pressure. Aircraft fly and perform on the basis of Q. You can feel this pressure when you put your hand out of the window of a car at speed. The dynamic pressure is about 10 pounds per square foot at 60 miles an hour. At 120 miles an hour, it is not twice as big, but 4 times as big, or 40 pounds per square foot. And that's due to that V squared term that you see there in the formula. The airspeed indicator measures Q and displays Q in terms of airspeed at standard sea level conditions. It has a square root function that makes the display nice and linear, but it is really just nothing more than a fancy pressure gauge. Finally, in all this preliminary stuff, you should have a feeling for what the lift and drag coefficients mean. CL, the lift coefficient, is simply the lift in pounds or tons or kilograms or ounces or what have you, divided by Q, which as you remember is a pressure, and then we multiply that by an area, usually the wing area. Pressure times area gives you a force, so the lift coefficient is a force divided by another force. So it is dimensionless, just a number. And that number would be the same under the same conditions whether we were using the foot-pound-second system or the metric system or any other system of units. The drag coefficient is very similar. It just uses drag instead of lift. So why would you use coefficients when we could just use the forces themselves? Well, the coefficients are almost independent of airspeed and air density, and they normalize for the effects of density and airspeed. You'll often hear people saying things like, extending the flaps increases lift. What they really mean is that it increases the lift coefficient at any given speed. Lift is pretty well always equal to weight, except in a steep turn. So it seldom increases or decreases, but an increase in lift coefficient means that the same lift can be generated at a lower airspeed. That's what they mean by extending the flaps increases lift. And while we're about it, let's just be clear what lift and drag are. Lift is the force perpendicular to the airflow, and drag is the force parallel to it. Note that lift is not always up. In this case, it's definitely not up. And lift always equal to weight either. In this particular case, it's a little bit more than the weight because it's at an angle like that. For completeness, I wanted to just mention two other ratios that affect the flying things and that you may come across. The first is Reynolds number, which is important for very tiny things like gnats and bumblebees, and it's a measure of the importance of the air viscosity. For a bumblebee, air is quite a viscous fluid, like oil, and it doesn't fly in it like an aircraft. Its flight is more like a swimmer treading water. At the speeds and sizes that we are operating, the effective Reynolds number is insignificant, so we ignore it. The other number we will neglect is the Mach number, which, as you know, is the ratio of the aircraft speed to the speed of sound. Mach is important as you get close to the speed of sound, which few light aircraft do unless there's something seriously wrong. The only parts that get to higher Mach numbers are the propeller tips. So here we are at last, about lift. There are two basic ways of holding up an aircraft. Where an aircraft itself is lighter than air, you have aerostatic lift, and that is free and always on. And then there's aerodynamic lift, which is what conventional aircraft use. And that lift is lift that you pay for, and the lift stops when the aircraft stops. So we will be concentrating on aerodynamic lift. When we think of lift, we naturally think of aircraft, but lift is a part of many things. A bird is pretty obvious. Birds use lift. Then there is the propeller. The propeller blades slice through the air and produce lift at right angles to the slicing that we call thrust. A sailboat with a wind abeam has a wing system that lifts the sailboat to windward. Then you get a windmill, which is a propeller in reverse, where an axial wind flow produces lift on the blade, driving the blade and hence the turbine. And then there is this very ancient device, the ship's rudder. Changing the angle of attack of the rudder lifts the stern of a ship round in the circle. And now for the million-dollar question. What makes lift in the first place? In your travels, you'll have doubtless seen a diagram similar to this one. The shape of the wing forces the airflow to higher velocity over the top of the wing than below, and Bernoulli's principle decrees that you get a lower pressure above the wing and a higher pressure below, and that provides lift. And all this is perfectly true, but what does all this sucking and blowing actually accomplish? So here's a clue. What's holding up that helicopter? In this picture, it's fairly obvious that what's holding up the aircraft is the fact that it's pushing large quantities of air down, and with Newton, the mass of air in the downdraft times its velocity gives the aircraft its lift. And what is due for a rotating wing close to the ground is also true for a fixed wing at altitude. Exactly the same physics holds. All airplanes are held up by their downwash. You can think of a fixed wing as being part of a rotor blade going round in a very big circle. The downdraft mechanism for a fixed wing is that high pressure underneath the wing and low pressure above produces a wingtip vortex at each tip, and the two of them induce a downdraft below and behind the aircraft. And most of the strangeness in behavior of aircraft, as opposed to other vehicles, can be traced straight back to the existence and behavior of that downdraft. So given that we have to continuously push air down to provide lift, is it better to work on lots and lots of air and hence a low velocity, or small amounts of air at higher velocity? Well, we intuitively know the answer, don't we? The helicopter on the left can hover for hours if necessary, working on its huge mass of air captured by those big rotor blades, and it throws down that air relatively slowly. The Harrier aircraft on the right is held up by Bristol Pegasus engines that blast quite small amounts of air at high jet velocities. To give you an idea, the jets consume about a pound of fuel per hour per pound of thrust. So if the Harrier were 100% fuel, it could hover for about an hour. In practical terms, the Harrier has to be lightly loaded to hover at all, and its hover endurance is certainly not more than about 10 minutes. Now, why does it make a difference to change the balance between mass of air and the downdraft velocity? After all, Newton says that they both have an equal effect in producing lift. That's true, but the thing is that once you've got your lift, the air that you've thrown down continues to contain energy that you've imparted to it in order to move it down. And the energy imparted to the air has got a v squared term in it. It's a half mv squared. So when you've got your lift and there's a block of air moving down behind you, the energy that is still trapped in that air and the energy that you provided is dependent on v squared. So it's much more efficient to provide lots of mass and little velocity than the other way around. So it seems important how much an airplane can grab to work on, how much air it can grab. And it turns out that the volume of air that the aircraft works on per second is approximately given by a circle drawn around the wingtips times the forward velocity. That produces a cylinder of air, and if you multiply that volume by the air density, you get a mass of air per second that the aircraft works on. And that determines the downdraft velocity we need to give us the lift we need to overcome the weight. What does that work out to, roughly? Well, let's take an aircraft with a 30-foot wingspan traveling at 150 knots, which is 250 foot per second at sea level, where the air density is 0.06 pounds per cubic foot. Under those circumstances, the airplane is working on 4,300 pounds of air per second. So it's a fair amount of air. So what we want is a long wingspan to increase the swept area and to travel at high speed to lengthen the cylinder. One aircraft that does both quite well is the U-2. Of course, it also flies at very high altitude where the air density is low, so it needs to handle the huge volume to stay up. So let's see what this famous downdraft does to a wing. Here we have a wing traveling horizontally at a high angle of attack. The airplane's nose is way up in the air. The airflow that the aircraft sees is horizontal because it's moving horizontally. But there's a downdraft at the wing. So the wing doesn't see a horizontal airflow, but a slanted one, because the free airflow gets added to the downdraft vectorially. So the effective airflow is coming in downwards from the left. What does that do? Well, one of the things it does is that it decreases the angle of attack. The wing is not working with the angle of attack that it looks like geometrically. It's working at a lower angle of attack because of that downdraft. And as we remember, lift is perpendicular to airflow, real airflow this time. The lift vector is rotated by the effects of the downdraft, and that induces that little blue drag vector at the top. The wing itself is pulling the aircraft back. That extra drag is called the induced drag, and it's the way the energy lost in the downdraft is manifested to the aircraft. That's the way the aircraft feels the energy that's imparted to the downdraft. So to summarize, the effect of the downdraft is firstly to reduce the effective angle of attack of the wing. And that reduced effective angle of attack directly causes the induced drag. You will have seen a lift curve similar to this one, I'm sure. The lift coefficient, remember that dimensionless quantity we talked about earlier, goes up linearly with the angle of attack until the flow starts to break away from the wing near the stall. A very, very long wing will have a maximum lift coefficient of about 1.6 at about 15 degrees angle of attack. But because a real wing is shorter, it operates in its own downdraft with its reduced angle of attack, so its lift curve looks less steep. The finite wing reaches about the same maximum lift coefficient, but it does so at a higher nominal angle of attack. Here's an extreme example of what I'm talking about. Both the Concorde and the glider are flapless, and they're both operating at about the same effective angle of attack, although they don't look like it. The short delta wing of the Concorde is producing huge downdraft velocity at landing speed, so the aircraft has to be at a very high nose attitude to get the geometric angle of attack that it needs. In fact, the Concorde is sinking rapidly here, so its geometric angle is even higher than it looks. Hence, of course, the famous droop snoots so the pilot can see for landing. The glider, on the other hand, with its long wing, is producing very small downdraft velocity, so it flies pretty well flat. The effect of the steepness of the lift curve has a big effect in bumpy air. Here we have two aircraft with the same weights and wing areas, but one has long thin wings and the other one has a short wing. Both are flying at the same lift coefficients, but at different geometric angles of attack because of downdraft effects. Now we get a gust. Because the aircraft are flying at the same speed, the gust increases the angle of attack for both aircraft to the same. But the effect in change in CL is quite different. The high aspect ratio aircraft sees a much bigger jump than the low aspect ratio aircraft. To give you an example, the Piper Cherokee range, with its short stubby wing, has a reputation as a very stable IFR platform, while an aircraft like the Diamond DA-40 with its high aspect ratio thin wing is considered skittish. This difference is often attributed to differences in wing loading, but in fact the wing loading on the Diamond is higher than on the Cherokee. The relative skittishness of the DA-40 is entirely due to its high aspect ratio. And if you've ever flown in gliders, you'll know that they're pretty lively in rough air. And then there is ground effect. What happens to all that air that we throw down? Does it continue downward forever? No, it eventually reacts against the ground, causing a local rise in pressure. In the case of this helicopter, it's easy to imagine that if you populated each square foot of the ground underneath it with thousands of pressure gauges and added up all the pressures time areas for the area under the helicopter, that it would add up to the weight of the helicopter itself, which is in fact true. That is absolutely true, but it's just as true for a fixed-wing aircraft at 35,000 feet as it is for a helicopter in ground effect. If any of you have ever been under the approach path when heavy commercial aircraft are coming into land, you can actually feel the increase in pressure in your ears as they pass overhead. Concentrate next time. It's not just the noise you're hearing, you can feel the pressure pulse. Now, the pressure pulse from an aircraft at altitudes is very, very diffuse, and it acts over a huge area with tiny increases of pressure by the time it reaches the ground. But in two special cases, that's not so. In the case of supersonic aircraft, the pressure pulse under the aircraft is locked in place by the fore and aft shock waves, so it doesn't spread out so much. You hear that passing pulse as a sonic boom. It's a double boom, one as the pressure suddenly increases, and one as it suddenly decreases as the pulse passes. The second case of ground effect is what you're more familiar with. When an aircraft is within about half the wingspan of the ground can be thought of as an aerodynamic mirror. The phantom aircraft flying upside down under the runway is creating a very real updraft into which the real aircraft is flying. So the real aircraft is essentially partially gliding in its own updraft, which results in a marked decrease in induced drag. So if you come in a little fast, you float and float and float in a low drag regime, just when it would be nice to have high drag so you can get down. Ground effect does have its uses in short and rough field takeoffs though. The other thing ground effect does is it changes trim. Particularly with low wing aircraft, ground effect helps with the round out. I will conclude this section with a short discussion of flaps. As I said, a cruise wing typically has a maximum lift coefficient of about 1.6. Using a split flap like on a simple GA aircraft does increase the maximum lift coefficient somewhat, reducing the stalling speed. But the most important effect is that the increase in wing camber increases the lift coefficient at any given angle of attack. This allows for reasonably high lift in a decent nose-down attitude, so we can see over the nose for landing. Concorde, not having flaps, has to land very nose high, and that's why they had to have the droop snoot for the pilot to see. Once you get to larger commercial aircraft, complex slotted Fowler flaps together with the leading edge slats really does pretty well double maximum lift coefficient to 3 or more. But the effect is not purely aerodynamic. When the flaps and slats deploy, the wing area increases substantially, so part of that high lift is simply due to a bigger wing. That concludes the section on lift. Our next lecture in the series will be on drag, where the downdraft also plays a significant part.